So I'm going to talk about algebraic definition of topological order, and I put the link in the chat, but I can no longer see the chat because of the screen sharing. So the link to the PDF is also on the slides. Um, so, so I originally thought I'd have to talk about some physics in this talk, but I think all of the physics has already been said, which means I could just get to do some category theory for you. My goal for the talk, Xiaogang in his lectures already mentioned this, that roughly speaking, the idea that I certainly learned from papers of Xiaogang's and Liang's is that um, we want to define a macroscopic notion of topological order as some sort of fusion n category, and with an extra axiom that I'm going to call, or that they call, remote detectability. So what I want to do for the talk is to kind of give you an outline of a complete mathematical definition of this. Because in 45 minutes, I mean, I'm not going to be able to give you sort of every single nut and bolt, but I want to give you a complete outline so that you could then go and fill in the details. So I've divided my talk into a bunch of little sections, and don't worry that I have 6 sections on the plan for the talk, because each section has like 3 slides. So I'll very briefly talk about weak n categories in general, and then I'll very briefly say something about our categorical condensations. Davide also mentioned condensations, and so did David this morning. Then I'll mention our definition of multifusion n category. I'll say something about remote detectability. I'll say something about like the difference between fusion and multifusion and braided fusion, and I'll end by saying what I can do in the way of classifying these. Already, I'll flag one other thing, which is that we sort of mentioned at the end of David's talk, that I'm not going to define what's actually fusion n category. I'm going to define what you'd call separable fusion n category. And I think that as we get more into the physics, the separability assumption is sort of natural there. Okay, so I want to tell you what a weak n category is, except I'm going to do this horrible thing, which is I'm going to give you a definition. I'm going to give it way too fast. So if you already know the definition, this will be a review, and you'll be like, oh yeah, I know that, and I didn't learn anything. If you don't know the definition, you're not going to learn anything because it's too fast. My point of giving this is just so that you can kind of believe that this can be done mathematically rigorously. The slogan, the idea of weak n category is the following. You want to define weak n category inductively. A weak 0 category is by definition a set. And then the inductive definition is that a weak n category is an infinity 1 category, whatever that is, enriched in the infinity 1 category of weak n minus 1 categories. So if you already know what a weak n minus 1 category is, well, if you know the whole infinity 1 category of those, and if you know the theory of infinity 1 categories and enriched infinity 1 categories, then you get the whole definition. So I'm not going to, well, I will implicitly actually tell you what an infinity 1 category is in the process of telling you this definition, but I will just give you kind of what this can unpack to. And I say can unpack to because honestly, there's lots of equivalent ways of realizing the words that I put on the slide of infinity 1 category enriched and blah, 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 blah. And I'm going to give you one of them. Is it the best? I don't know. It's the one I could fit on 3 slides, and there are 3 slides that I take. And I should also say the fact that we have a definition doesn't mean that everybody has like a complete grasp. Like there's a lot to explore about weak n category, but at least there is a mathematical definition. So let me unpack it for you. A weak n category consists of the following data. There's a set of objects called the objects of C. Our category is going to be called C. And then for every list of objects, for every non-empty list of objects, x0 through xk, part of the data of the weak n category is an n-1 category, a weak n-1 category of composable k-tuples of objects. I mean, I call it the n-1 category of composable k-tuples, but it's just part of the data. It's like an assignment of an n-1 category for every list of objects. And since by induction you already know what an n-1 category is, so I didn't have to tell you what that was. You worked that out already. And then, but you should think of this as this is the collection of all ways of listing k many composable morphisms. And then these sets, these n-1 categories, basically form some sort of simplicial structure. I'm not going to go into detail of what a simplicial object is, but you can learn about it. The basic idea of a simplicial object is that there's some maps. There's a map every way you could delete an element in the list, and there's a map every way you could repeat an element in the list. And these maps have some compatibility well, there's an obvious compatibility. If you delete one element and delete another element, it shouldn't matter which order you delete it in. If you repeat an element and then delete one of them, that should give you the identity. So that's the data of a weak n category. It's this data. Now I need to give you some axioms to make it behave correctly. So I've already said that deleting an element corresponds to composing. If I say take two morphisms, so if I take the category of all ways to go from x0 to x1 to x2, and then delete the middle spot, I'm supposed to take the map that took me from a pair of morphisms to just one morphism, to just their composition. The main axiom I need is that that having a pair of morphisms is the same as having a pair of morphisms. So in my axioms, I said that there's a category, an n-1 category of pairs of morphisms, and more generally an n-1 category of k-tuples of morphisms. Well, using the simplicial data, you can take any n-tuple of morphisms, any k-tuple of morphisms, and write down all of the components of it. So that is a big map from the space of k-tuples to the product of the spaces of individual morphisms. I don't demand that map be an isomorphism of n categories. Instead, I demand that be a weak equivalence of n categories. And now you should say, oh, but you haven't told me what a weak equivalence is. See, I'm doing an inductive definition, but hold on a moment. If you did know what a weak equivalence was, then there's a standard way of producing composition maps. You say, I take, say, a map from x0 to x1, a map from x1 to x2. The space of pairs of those is not the same as, but weakly equivalent to the space of pairs of maps for my definition of pairs of maps, and then I can compose. And the idea is that this doesn't give you a single composition map, but it gives you a contractible space of composition maps, and then you get a composition, and then there's standard arguments that this composition is associative up to higher coherence. Okay, so now I have to tell you what a weak equivalence is. Well, it's totally obvious what a strict functor is. It's just a map on objects to objects and a map and strict functors on their spaces of morphisms. Strict functors are not the right thing to use, but you can write them down. And then what you say is you define a weak equivalence to be a strict functor, which is fully faithful and essentially surjective. And the notion of fully faithful requires that you know what weak equivalences are of n-1 categories. But see, this is the beauty of the definition. To define n category, you have to know everything about n-1 categories. But you don't have to know anything about n category until you're trying to define n category. So, okay, you can ignore the whole definition. I put it on the slide so that you believe it exists. The point is that there's a good theory of these. If you like these things, you can build a model category. If you don't like these things, it doesn't matter what a model category is. Model categories are just some tool that people like Claudia use to know that everything is actually going to work correctly and smoothly. For most people, some people care about n categories, and that's great. That's like the computer programmers of category theory. And the computer users of category theory just have to know that a weak n category is something with morphisms in dimensions 0 through n. The n morphisms are form sets, and their composition is strict. And in all dimensions less than n, the compositions are not strict. They're strict up to higher coherence. You can just as easily define C-linear weak n category by making the spaces of n morphisms into C vector spaces. Okay, that's the definition. Now you should forget it. So now I'll get to the first thing in my actual talk. So the reason you should forget that whole definition is because honestly, most of the time you can ignore all of it. Honestly, most of the time when you work with higher categories, or not most of the time, some of the time you really have to care about higher coherence, and some of the time you can completely ignore all this like associator and homotopy stuff. One of the times you can completely ignore it pretty much is when you're working with structures that are parameterized by what are called Gaunt n computets. It doesn't really matter what Gaunt n computet is. It means that the structure itself never uses is a really kind of very easy object. And an example of this is our notion of condensation, which is what I really want to tell you about. So David already said basically what this was this morning, so I will say it really quickly. So a condensation from, in an N category, again, I'll define it inductively. It's a condensation is it's our higher categorical version of split surjection or of retract. These are like the projections on the direct summits. And so what I want is a condensation is a map from X to Y, another map from Y to X, which is the splitting. And then if you were in a one category, you would say that, well, going down and back up is, no. If you were in a one category, to say it with a split surjection, you'd say that going up and back down was the identity. Instead, I said that going up and back down condenses to the identity. And if you made it to the first kind of the Monday of the conference, Davide also explained why we invented this. So this is a notion that we invented, that Davide Gaiotto and I invented, but David Ryder and Chris Douglas had invented the two category version for it. I want to use this as a chance to advocate a notation that we like, which is an arrow with a little hook on it. There's no, the literature, split surjections and retracts appear like throughout the category literature, and we need a universal notation for it. And so I came up with one, and I want you to use it. But so that's what a split surjection is. You can explore it in detail, and I've spent whole hour-long lectures exploring it. But that's not what I want to focus on. As I said, David already explored it a little bit this morning. As soon as you know what a split surjection or a condensation is, well, in one category theory, if you know what a split surjection is, then you also know what an idempotent is. An idempotent is something that squares to itself. And going through the same logic lets you take the notion of condensation and produce a categorified version of idempotent. David told you this morning what it was. It's basically a separable monad, or rather a non-unital separable monad is the best description. So it's an endomorphism, which instead of squaring to itself, its square should condense to itself, and that should have some associativity. There's a natural notion of splitting. And this is how we define the Karoubi completeness of higher categories. And again, I'm not going to focus on this in my talk. I just wanted to say it so that you believe that everything can be done kind of completely rigorously. Our theorem with Davide, and again, everything was done by Chris Douglas and David Ryder when it is to, is that our notion of Karoubi completeness is the right one. That's sort of the takeaway of our theorem. That first of all, the notion, if all of these are supposed to generalize statements in one categories. So if a condensation monad splits, if an idempotent splits, the splitting is unique up to unique isomorphism. There's a natural Karoubi completion that completes any category. I'm going to use the words condensation completion and Karoubi completion completely interchangeably in my talk. In fact, if you're already Karoubi complete, then you're complete for all absolute colimits. I'm not going to tell you what an absolute colimit is, but if you already know what it is, it's the same thing in higher categories as it is in lower categories. And moreover, the construction so the most important part of the theorem is that there's sort of, now you can do an iterative construction. You can start with vector spaces. And for me, I always mean finite dimensional vector spaces. That's a symmetric monodal 1 category. You can produce from it a symmetric monodal 2 category which has only one object, and vector spaces as the category of vector spaces as the endomorphisms of that object. I think we saw this construction on Wednesday, actually. And now you can take that 2 category with one object and complete it for all condensations. And that produces another, a larger 2 category, which is what I'm going to call 2 vector spaces. Now you can repeat. You can take a 1-point delooping, and then you can complete it to get 3 vector spaces and so on. Our theorem is that this construction, this iterative construction, produces the fully dualizable subcategory of all C-linear categories. And that's a sort of important theorem in the second half of my talk, or the second 2/3 of my talk. And I should put a caveat. I'm confident about our theorems, but our theorems use some statements about colimits in enriched higher categories. These are sort of technical statements. We don't use a lot of the story of colimits and enriched hierarchy categories, but we use a little bit of it. This story has not been written. In the paper with Kyoto, we say exactly what we need from that theory, and we basically kind of define the words so that those to define that the parts that we need ends up being true. But it would be much better for eventually a complete understanding of colimits and enriched hierarchy categories to be worked out. But all we need from it is stuff that's like really, really well understood in lower categories, and we assume it's going to hold true.
Excuse me, I have a question here.
Yes.
For example, for the 3-vec.
Yes.
3-vec, and how many simple objects are there? Is that a 1 or infinite labeled by integer?
How many simple objects are there in 3-vec?
Yeah. Yeah, those are membrane objects in physics, some kind of membrane.
Right, so those are good questions. So
three-dimensional space.
So let me answer the question already. Let me go through it and you'll see what happens. So in 1-vec over a field, there's only one simple object. Of course, that's the one-dimensional vector space. In 2-vec, the simple objects are indexed by the division rings over your fields. So over the complex numbers, there's only one, but already over the real numbers, there's 3 of them. There's 3 simple objects in 2-vec.
Oh, I see. A complex number is 1. Okay, yes.
Right. In 3-vec, so in 2-vec, the objects are separable associative algebras. So the simple objects are simple associative algebras, which is to say division rings. In 3-vec, the objects are multifusion categories. And so the simple objects are fusion categories, as we learned from David this morning.
Yeah.
And so there's a lot of simple objects. There's one for every fusion category. And actually, Morita equivalent fusion categories sort of become isomorphic objects. So there's one for every Morita equivalence class of fusion category. But that's still a lot.
Okay, yeah, thank you.
So physically just means include all non-chiral topological orders in the 3-vec.
That's right. So our theorem with Davide is that 3-vec is also the space of well, I told it to you in terms of TFTs. It's the fully dualizable subcategory of something or other. And our theorem with Davide also expresses it in terms of like topological orders that admit a nice enough boundary condition.
Okay.
In particular, the boundary condition's gapped, and maybe that's all it needs over the complex numbers, and maybe over a field of positive characteristic, there'd be a little bit more. Okay. And so these are like non-chiral in the sense that they admit a gapped boundary.
Yeah, thank you.
And also the morphisms between them have to admit gap boundaries. Okay, so now I get to tell you what I actually want to tell you about in the talk, having sort of flashed those definitions way too quickly. So I'll slow down a little bit. So David this morning already told you what a multifusion 2 category was over the complex numbers, and I'll review a little bit of the logic and also tell you more generally what a multifusion n category is. And this is like the first ingredient in giving a definition to the words that Liang and Xiaogang have asked for about kind of fusion n categories with remote detectability. So I want to motivate the definition. So let me remind you what you already know about 1 categories. A multifusion 1 category is a definition of multifusion 1 categories. A multifusion 1 category is any monoidal C-linear Karubi complete category, which has 2 important properties. One is that it's semi-simple with finitely many simples. So that's just something about the underlying category of the fusion category, of the multifusion category. And then the second property is that as a monoidal category, it's rigid, meaning that every object has a dual. So property 1 only sees the underlying category of your monoidal category. Property 2 uses the monoidal structure. So now I want to tell you a generalization of these two axioms to higher categories. So to do that, I need to rewrite them slightly. So in a sort of way that doesn't reference so much the fact that I'm in a 1 category. So the first rewriting uses by now old results of Ulrike Tillmans from her paper on Chern-Simons theory. So what she shows is that one category, forget that it's monoidal. If you have a one category, it's a Caribe complete C-linear one category is semi-simple with finitely many simples if and only if it is dualizable, one dualizable in the space of Caribe complete linear categories. And this also happens if and only if it's actually fully dualizable, two dualizable in this two category. So those, either of those being like one dualizable or being fully dualizable are good replacements for the notion of semi-simple with finitely many simples. I'm going to call a one category with these properties, I'm going to call it proper, but you could call it finite dimensional or fully dualizable or whatever you want. So that's the first generalization, or the first sort of rewriting it. I can rewrite number one in terms of dualizability information. So rewrite number two, I need to sort of say something about categories with duals. So this is a great exercise. I highly recommend it. I learned it, I don't remember really where I learned it, but I think it's being cited to notes of Gates-Gorey, at least in the literature being attributed to him. Maybe it's due to him. Which is that if you have a monoidal category, saying that that every object has a dual is essentially the same, and there's like some footnotes in what I'm saying, but it's basically the same as saying that it is the same for the categories I'm carrying for these sort of semi-simple finite many simples categories. Saying that every object has a dual, well, see, I want to go through the argument a little bit. So I have the multiplication map. I have the tensor structure from A times A to A. The fact that it's associative, one of the ways to say that a multiplication map is associative is to say that the map multiplication from A times A to A is actually a map of bimodules. It's an A bilinear. Now, because my underlying category is semi-simple with finitely many simples, this functor automatically has an adjoint at the level of a functor. What Dennis shows is that your category has duals if and only if the adjoint functor, which I'm going to call delta, is actually an A bilinear functor. So it's a map of bimodules. And I call it delta because it's like having a you should think of it as like the co-multiplication in a Frobenius algebra. So just to repeat, I know I said this already and it's on the slide. One of the ways to say that a category has duals is to say that the multiplication functor has an adjoint which is A bilinear, an adjoint in the category among A bimodules. And I'm not going to use the fact that of an adjoint. I'm just going to use the fact that that there's a co-unit of this adjunction, and that the co-unit of the adjunction is A bilinear. So now I need to generalize one more time, or use one more sort of actually kind of hard theorem, which was something we discussed a little in the break after David's talk this morning. Using that I'm in characteristic 0, this doesn't hold in positive characteristic, but in characteristic 0, you can show a little bit more. In characteristic 0, you can show that the co-unit of this adjunction, this map eta that I've written down, can be split. So what you can show, the way David would say it this morning, is that this adjunction is actually a separable adjunction. And so fusion category for which this adjunction is a separable adjunction, that's called a separable fusion category. It's equivalent to a separable fusion category. As far as I can tell, it was Douglas, Schomer, Priest, and Snyder who gave the complete proof that every fusion category in characteristic 0 was separable. And so to summarize, at the end of the day, a separable, I'll also use the word smooth, I'll use those words interchangeably. To summarize, separable multifusion, one category is a monoidal C-linear one category, which is Caribe complete, which has a kind of underlying the category is dualizable, and also the multiplication map is an A bilinear condensation, an A bilinear separable adjunction. So that's the definition. That's a definition of separable fusion one category. And this is a definition that generalizes very well to higher categories. So now I'll tell you, so just to repeat the definition, but now I'll say change all the numbers 1 to n. So a separable multifusion n category for me is going to be a monoidal C-linear Caribe complete n category, which has two properties. It should be proper, meaning that the underlying n category of my like forgetting the monoidal structure should be one dualizable among Caribe complete n categories. And my theorem with mine with David Kyoto is that actually it's automatically fully dualizable. It's automatically n+1 dualizable. So that's like a version of Tillman's statement that one dualizable implies two dualizable. And then the other axiom I want is that it be smooth, meaning that the multiplication map is not just an A bilinear map, but actually extends to an A bilinear condensation. So I'm defining a multifusion n category as a smooth and proper monoidal Caribe complete linear category.
For you, Theo, about
yes.
You're saying extends to an A bilinear condensation. Is that just a property, or is that extra data that needs to be provided?
It's just a property.
Okay.
But the reason it's just a property is because the extension is unique in a sort of suitable sense.
Okay, great. Thank you.
Like there's a natural category of possible extensions, and that category is contractible or empty. I mean, you have to say it correctly, but
thanks.
Yeah, that's sort of section 3 of my paper with Davide. Is that uniqueness. So anyway, then our theorem, something that I'm sure that many of you probably have heard sometime, at least if many of you are Claudia, is that an associative algebra is fully dualizable if and only if it's smooth and proper. And my theorem is that in this world of Caribe complete n categories, the same is true. That a monoidal C-linear Caribe complete n category is two dualizable if and only if it's smooth and proper. And it's also fully dualizable if and only if it's smooth and proper, namely it's n+2 dualizable. And what I'm calling more 1 is what Claudia called alg1, except that what I'm calling more 1 is the unpointed version, and that matters only to Claudia. And I should say this fact that two dualizable implies fully dualizable, this is kind of peculiar to the fact that I'm using C-linear Caribe complete and no further completeness. Dualizability questions depend a lot on how complete your categories are. The more you complete a category, the easier it is to write down co-units of adjunctions because you get more and more objects. And the harder it is to write down units of adjunctions. And so, maybe I have this backwards. The more complete you are, the easier it is to write down the unit of the adjunction, the harder it is to write down the co-unit of the adjunction. And so, being able to jump all the way from 2 to fully is because I'm in this sort of barely complete, just Caribe complete, no further completeness. Claudia conjectured in personal correspondence that that the fully dualizable objects of any reasonable n category is always the same and depends only on n, but the two dualizable objects are different.
What did I conjecture?
Claudia's conjecture, which you told me in Edinburgh a year or 2 ago, was that any reasonable thing that deserves the name n vector spaces, its fully dualizable subcategory should be independent of how you understood the word n vector spaces.
Oh, I see. Yes.
So
okay.
David mentioned this conjecture this morning, for instance.
Which is proven for n equals 2, more or less.
It's proven for n equals 2 for a long list of possible reasonable categories, not for all of them. So anyway, so from a fusion n category, I can already give you a fully dualizable object in an n+2 category, which it means is the same as an n+2 dimensional frame TFT by Murray's theorem. And this is the TFT that Xiaogang calls the anomaly of the corresponding fusion category. That use of the word anomaly doesn't quite match what people who grew up learning math from Dan Freed used, but it's Xiaogang's name for it. So, okay. I'm going to go on, but feel free to interrupt me. So I want to say something about remote
Can I ask a
detectability.
question?
Yes.
Hi. So I have a question about the word rigid in the previous slide. So
Yeah.
for ordinary fusion categories, there is a theorem about Oaknian rigidity that that fusion category don't admit any deformation,
Right.
any continuous deformation.
That's a much deeper use of the word rigid. This word rigid, I think, is sort of the Australian school's notion of, it just means having all duals. I'm not sure why it's called rigid.
So does that criterion of that they don't admit any continuous deformation also applies to your definition of higher, like two fusion categories and so?
That's a great question. I haven't considered it. I have no idea. My understanding is Oaknian rigidity is a sort of subtle, deep thing, and so I wouldn't be able to answer it off the top of my head. But if you made me bet money, my bet would be that for n, say 3 or less, it's still rigid, and that for n large enough, probably it's not.
I see. Thank you.
But I'm not willing to put very much money on that, and I feel like I'm being recorded, and maybe I should be careful about making wild speculations. So it's a great question. Okay. So there's one more ingredient that Xiaogang and Liang ask for in their definition of n+1 dimensional topological order, which is that they ask for a remote detectability hypothesis. And the physics of this is that, as Xiaogang explained on maybe Monday or Tuesday, is that any excitation. So okay, what's going on? One of my fusion n categories. This is organizing all of the operators, all the excitations in an n+1 dimensional topological order, including all the extended operators of any dimension. So suppose you have some system, you insert some operator. Now we're doing physics. You should be able to tell by doing some experiment that you did that insertion. Well, the only way you could tell it is by inserting some other operator and testing against it. And so when you try to kind of work through that logic, you would say, well, so that's this remote detectability. I should be able to detect any operator insertion with some sort of remote probing by inserting some other topological operator. And one of the ways to try to say this mathematically is to say that the Drinfeld center of my fusion n category should be trivial. The Drinfeld center is not a hard thing to write down. It's if you have any monoidal n category, whether it's fusion or not, if you have any monoidal n category, its Drinfeld center is by definition the n category of a bimodule endomorphisms of your object. This is just automatically C linear and Karubi complete. It sort of automatically has all completeness that your original category had, just because you can write it down as a limit. And so I have this sort of for any monoidal n category, in particular for a multifusion n category, I have a Drinfeld center, and my axiom is going to be that I would like to request, I'll say that I have remote detectability if this center is trivial in the way it can be, which is to say it is only the n category of n vector spaces. As we were discussing with Xiaogang already, when n is 3, that n category has lots and lots of simple objects. So it's not really trivial. It has a lot of things in it, but they're things that you would automatically universally have. So my theorem is then the following. My theorem is that a multifusion n category, under this multifusion hypothesis, under this dualizability hypothesis, being a multifusion n category, so having trivial center, is the same as being not just dualizable in the n+2 category that Claudia explained to us this morning. And this should say Karubi complete categories. Sorry, I left that off the slide. Not just that you're dualizable, but actually that you're invertible in this n+2 category of this Marita n+2 category. And the invertibility of the anomaly is when Freyd says that something has an anomaly, he means that there's sort of an inverted, that you're not just relative to something, but an invertible thing. And so a corollary of this invertibility hypothesis, of this theorem, is that actually my definition of algebraic topological order matches the space of well, not the space of n+1 dimensional TFTs, but rather the space of anomalous TFTs, in the sense that they're not fully extended objects in and of themselves, but they have some invertible. There's like an invertible n+2 dimensional theory, and that these are attached to this. Okay. So that completes the definition of that Xiaogang and Liang and their collaborators have asked for of multifusion n category with remote detectability. And now I want to talk about some more what I think are actually sort of more interesting results that I was able to prove. So the first thing I want to talk about is going from multifusion to fusion. So if you ask what is the physics of a multifusion n category, well, let me say what the okay, I'm going to say things that aren't quite in the order of the slide, and I apologize. Xiaogang emphasized at the beginning of the week that he doesn't really want multifusion categories. He wants fusion categories. And the reason for this is the following. If you have a topological order, at least if you're over the complex numbers, which I'm going to be. So if you don't have any, like, you're not protecting by time reversal symmetry or something like that, then you might have thought that you had a so what I want to say is the following. There's, in high energy, we'd call it the space, there's a sort of space of local vacua, or a set of local vacua that you can write down for one of these. And I'll give the math in a moment. But as soon as you have multiple local vacua, this is what a high energy theorist would call a local vacuum, is what Anton in the beginning of the week would call the space of ground states in infinite volume Rn. If you have multiple local vacua, then your theory is sort of unstable against deformations. You can modify your Hamiltonian by a small operator to condense your theory onto any individual local vacuum that you wanted to. So the mathematics here is the following. If I have a multifusion n category A, I'm going to write omega A, the loop space of A, for the endomorphisms of the unit object. That's automatically a multifusion n-1 category. My multifusion n category is supposed to be all the excitations in my topological order. The loop space of A is all the excitations that have so all the excitations that have codimension at least 2 in space-time. And continuing on, I could keep looping and looping. So you could loop all the way to the top. You could just look at the zero space-time dimensional excitations, the vertex operators in your theory. This will always be a commutative algebra, and it may or may not be one-dimensional. And the spectrum of this commutative algebra is what a high-energy theorist would call the set of local vacua in your theory. Multifusion category, for me, will be called fusion exactly when this commutative algebra is just the complex numbers and not of higher dimension than that. And this matches, so another way to say this, equivalently, I'm saying that the identity object in my multifusion n category does not decompose. In a fusion n category, the identity object should not decompose as a non-trivial direct sum, which is how David defined it this morning. So that's the difference between multifusion and fusion, is this sort of indecomposability of the identity object. And now I want to tell you kind of the theorem I'm perhaps the most proud of in this story. My theorem is the following. If you have a multifusion n category, which satisfies remote detectability, then the following two things are equivalent. So on the one hand, you could ask, is it or is it not fusion? On the other hand, you could ask, do you or do you not need to know the codimension 1 operators? To make this more explicit, let me say this just when n is 2. So I'm doing 2 plus 1 dimensional topological order. Maybe all the way in the maybe like roughly 1990, I'm not sure. Xiaogang explained that 2 plus 1 dimensional stable topological order, meaning that the ground state, that there's sort of, it's stable against this kind of adding a small operator, is that those are classified by essentially modular tensor categories. I have to tell you just the line operators in the theory. Now, there are surface operators that you can build from this condensation procedure, but the point is you don't need to tell you them. So my theorem says this in general, that if all of your vertex operators are trivial, then also all of your codimension 1 operators are somehow trivial. You have to take this really carefully, because there really are codimension 1 operators, like there's lots of indecomposable ones, but they can all be built from condensing networks of codimension 2 operators in higher. The naive argument for this is that if you wanted to detect a codimension 1 operator, you'd have to detect it by kind of having a commutator. And well, one of the ways you could detect a codimension 1 operator is to detect it by looking at its commutator with a vertex operator. You either insert the vertex operator on one side or you insert the vertex operator on the other side. And so the fact that you have no vertex operators should suggest to you that there's also no codimension 1 operators. But that argument is sort of, doesn't work all the way, because maybe you could have detected it by commuting it with sort of a larger operator. And the theorem says that is what it is. The main step in the proof is a more general result that is somehow well known in the 1 category literature, and I showed it for n categories, which is that the functor from the center of your algebra from the center of your fusion category to your fusion category is always dominant, meaning that every element in my fusion category is the condensation of things in the image of the center. And if you can prove that, then you can prove the rest of the results. So that's the hint to the proof. You can do this actually for any amount of any categoricities. So the slogan is that if all of your excitations of dimension at most k are trivial, then all of your excitations of codimension at most k plus 1 are also trivial. And always with a grain of salt on what trivial means. You're always allowed to take, when I say something's trivial, I just mean that that it arises from condensing lower dimensional things. The theorem, I put the theorem on the slide. If the n minus k-fold loop space of A is trivial, then A is the k plus 1 fold suspension of its k plus 1 fold loop space. And this is under the condition of having remote detectability. And the proof's essentially the same thing. You have to develop a theory of higher centers, at least write down the definition of a theory of higher centers, and then show that some functor is dominant. Okay. So I have 2 minutes left, so now I can tell you why I cared about these things. The reason I cared was the following. So again, I'm going to say this, well, okay, I'll say this in the order of the slide. So again, I'll repeat the slogan. The slogan is that if all excitations of dimension at most k are trivial, then all trivial, understood correctly, then all excitations of codimension at most k plus 1 are also trivial. So let's take n now to be 3. Let's look at 3 plus 1 dimensional topological orders. And I want to take k to be whatever it is, 1. So what I'm saying is that if you have a 3 plus 1 dimensional topological order with no line operators, or at least no non-trivial line operators, of course there's the identity line, there's sums of the identity line, then also it has no surface operators. And I don't mean no surface operators, I mean no non-trivial surface operators. No surface operators that you can't build from condensing the vacuum line. And this statement is the one kind of, I think, hole in a really inspirational series of papers by Lan Kong Wen and by Lan and Wen that I spent a couple of years really thinking hard about. And it's why I was really trying to do this. So their theorem was a classification of 3 plus 1 dimensional topological orders. And they said with a fair amount of fine print that every 3 plus 1 dimensional topological order is canonically a topological sigma mod. And I was very dubious of this. I think a lot of us were very dubious of this announcement when it came out, and we all sort of tried to study it. And what it sort of, I think the one gap in the proof was this statement about that they sort of used this sort of naive idea that if there were no line operators, then there were also no surface operators. And this was the one thing that really needed to be proven. And I put some small prints on the page that I don't have time to tell you about what exactly I mean by anomalous topological sigma model and about fermionic versus bosonic theories. And I'm out of time, so let me just say that, let me say very quickly that kind of I can push this type of logic of theirs to some higher dimensions. So let me just quickly run through what my definition means in all dimensions. In 0 plus 1D, as we were saying, we're talking about matrix algebras. Really, we're talking about central simple algebras, which are the same as matrix algebras up to kind of a U1 ambiguity. As Xiaogang told us on Monday or Tuesday, I don't remember, in 1 plus 1D, all topological orders are unstable. You can always collapse your theory onto a single local vacuum. Fermionically, there's still a little bit of data if you have a 1 plus 1D unstable theory, that if you might have two local vacua and they could either have the same relative Arf invariant or a different relative Arf invariant. In 2 plus 1D, we're looking at basically multifusion, modular tensor categories. The classification of modular tensor categories is wild. I don't think we're ever going to do it. In 3 plus 1D, we just have topological sigma models with one groupoids as targets. It's kind of classification is only as hard as the problem of classifying finite groups, which of course is wild, but it's much easier than, say, all modular tensor categories. In 4 plus 1D, I'm working with a PhD student at Perimeter named Matthew Yu to classify theories. I think I know what the answer is. I think it has to do with symplectic finite abelian groups. In 5 plus 1D, the Lan Kong Wen proof basically goes through as soon as you can do two categorical Tanakian duality, which I think I know how to do with my Kopkins. In 6 plus 1D, I don't know. I think it has something to do with the classical Witt group. And in 7 plus 1D, you would need a three categorical Tanakian duality. I should have said, the other main step in the Lan Kong Wen proof is some Tanakian duality arguments about existence of fiber functors. And these, I think, work in 5 plus 1D and definitely don't work in 7 plus 1D. And that's the end of my talk. I'm sorry for going over. Thank you.
Thank you very much. And any quick questions? Otherwise, I guess we.
I just have a short question.
Sure.
So in 3 plus 1D, in your classification, include this case with fermionic charge, or it's still possible?
So the cleanest way to state the classification, so as I said, there were these pair of papers that were really inspirational, and then I spent some time trying to kind of clean them up. And the cleanest, well, the mathematically cleanest way to state it, maybe not the physically cleanest way to say it, is to give the classification first for fermionic topological orders. And the statement there is that a fermionic 3 plus 1D topological order, completely canonically, what you can do with any fermionic topological order is, so this was the small prints I skipped over. If you have a fermionic 3 plus 1D topological order, what you can do is you can look at its category. So this omega 2 of A is the line operators in your theory. That's automatically a symmetric monadal fusion category. And then what you can do is you can study what I'm going to call the spectrum of this fusion, symmetric monadal fusion category. It's not, because I'm fermionic, it's a superfusion category. And so the spectrum is, well, the spectrum of an algebra is, and I really should call this like the C, anyway. A kind of poor person's definition of spectrum of an algebra is that it's the set of maps from the algebra to the complex numbers. And a poor person's definition of the spectrum of a fusion category is it's the groupoid of maps from your symmetric fusion category to supervector spaces. And the actual understanding, if you really sort of think very carefully about Tanakian duality, what Tanakian duality tells you is that this groupoid is a kind of complete invariant of your symmetric fusion category. So I mean, you really are like the categorified functions on this groupoid. So that's part of the data of the classification is this groupoid. It will become the target of the sigma model. And then the action of the sigma model is a supercohomology class on this groupoid. And it's not really a supercohomology class, it's really a reduced supercohomology class because of this issue with anomalies. Every reduced supercohomology class in this can enhance to a supercohomology class, but not quite canonically. And I need to be using reduced cohomology to make the classification canonical. So that's the classification for fermionic theories. For bosonic theories, there's a little bit more information, and the kind of mathematically clean way to say this is to say it in terms of descent data for fermion parity flip. And then you have to invent kind of twisted equivariant reduced supercohomology. And when you kind of, that basically at the end of the day kind of packages the classification from these papers by Lan Kong and Wen about whether or not they're emergent fermions. But if you know those papers, they had a kind of complicated classification that's like, well, you do this if there's no emergent fermions, and you do this if there are emergent fermions, and you do this if something else. And this is a kind of way of packaging it in categorical mumbo jumbo.
So, so in terms of physical language, can I say it's just like a gauged SPT phase, or there's something beyond that?
Well, I don't know. It depends on how much just like means just like. The fact that I'm using supercohomology means that I really do have to think about, like, it used to be when people said SPT, maybe they thought that SPT phases were classified by just ordinary cohomology. And that's just not true.
Yeah,
SPT phases.
Yeah, for fermion, you need this supercohomology.
Right. So for fermionic theories, we know you need supercohomology, and more generally, I mean, this is because supercohomology is a kind of an approximation in this dimension to cobordism.
Right.
And so, but as long as you're willing to kind of take that understanding when you say SPT, then it kind of goes through, except for the fact that these are reduced classes and not honest cohomology classes. And that really doesn't matter if you're fermionic that much, but for the bosonic theory, it matters a little bit. So what's going on is that, okay, this is something I haven't finished a proof of, but I think every condensed matter theorist will tell you that there are, so for instance, you can ask, what are all of the, so here's the place where you can see the difference. You can say, what are all of the 3+1D topological orders whose line operators consist of the vacuum line and a fermion? So these look like they're supposed to be Z2 gauge theories, except that in a Z2 gauge theory, the electrically charged particle is a boson. And now I'm asking for sort of something like a Z2 gauge theory, except the electrically charged particle is a fermion. And I believe I can prove that there are exactly two of these, one of which is not anomalous and one of which has a, so these are bosonic theories where the Z2 gauge, where the electrically charged particle is an emergent fermion. And I believe that I can prove that there's exactly two of these, and one of them has an anomaly, and that's like basically a 5-dimensional Stiefel-Whitney class. It's like the W2 times W3, I think is the anomaly.
You mean the point charge is fermion? That's anomalous?
Yeah,
or?
So I want a bosonic theory for which the charged particle is an emergent fermion. Anyway, when you try to set that,
in this string-net construction in 3+1D, it's kind of related to symmetrical category, right? So you can make the toric the charge to be fermion.
Yes. So the point is that there are in fact exactly 3 theories where there's one charged particle for a Z2 field. One of them is the sort of straightforward toric code in 3+1D, where the electron is a boson. One of them is kind of string-net model where the electron is a fermion, but it's still not an anomalous theory. You could still write it down as a kind of totally in 3+1D as a commuting projector Hamiltonian model. And then there's a third one which has an anomaly. So it does not really live as a true 3+1D model, but rather it lives as a boundary condition for a 5D invertible phase.
I see.
And all of this stuff about reduced blah 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 is to catch that last example.
Okay, thank you.
Was there a question by Shutdown, or Shutdown lower their hand again? Okay. Anyway, I guess.
Yeah, I'm fine. I'm fine. Thank you.
So, Cecile, I just have one thing to confirm. I think your theorem that remote detectability implies fusion, it doesn't hold in one dimension, right? So it doesn't hold for fusion 1 categories. So because there are really multi-fusion 1 categories with trivial center.
So sorry, let me say the theorem correctly. The theorem is that if you have remote detectability, then you are fusion if and only if you are what I would call the suspension of your loop space. So let me unpack this in 1+1D. So in 1+1D, I'm talking about multi-fusion categories with trivial center. There are plenty of multi-fusion categories with trivial center. Now the loop category of a multi-fusion 1 category is just the endomorphisms of the unit object. That's just a commutative algebra. And the suspension of that commutative algebra doesn't see the whole multi-fusion category.
Okay.
It just sees like.
So the second one is not satisfying.
That's right.
Okay, I see.
Yeah, so what's going on here is that a multi-fusion N category is not just like, I think some people like me when I was younger thought that if you had a multi-fusion category, just a multi-fusion 1 category, well, I was like, okay, I have a multi-fusion 1 category. I know that the endomorphisms of the unit object are a commutative algebra. Maybe I can use that commutative algebra to break up every object. And you sort of can. Every object decomposes as a sum parameterized by the spectrum of that commutative algebra. But the decomposition is different depending on whether you act from the left or the right. And that's the thing you have to remember. And so there are, what's going on is the following. In 1+1D, if you have multiple local vacuum, if you're a multi-fusion N category, then you have a bunch of different kind of local vacuum, a bunch of different local ground states. And there are infinitely massive excitations between any pair of them. And in high energy, those were like heavy, but not infinitely massive, and they flow down. And the part of the data of the multi-fusion 1 category is those excitations that let you tunnel from one local vacuum to another local vacuum.